We're starting chapter 8, hypothesis testing, and this can get pretty confusing. So this first section is just kind of an introduction and some terms and the testing of how what all this means. We're only going to do the first few sections in chapter 8, so we're not going to worry about the z-test for proportion. That's a wrong symbol, but a test for variance, standard deviation, we're not going to worry about those. And so the first few objectives, excuse me, are the ones we're most concerned with, especially in this first section. We will go through objective 4, state the 5 steps used in hypothesis testing and finding the critical values, and what the null and alternative hypothesis is. I'll go through that. Now, hypothesis testing. When a researcher does research, they're testing a hypothesis, and they have to know if what they were working on, for example, if it's medical research and they're testing a medicine, they have to know if it made a significant difference or if the differences could just be accounted for in the variation of the mean. In other words, what we did in chapter 7, you remember we found a range where the mean of a population could normally fall within. It could be between, a low value and a high value, and that would be normal for a mean of a sample to fall within that range. And so when we test a hypothesis, we want to know whether this made a difference because of what we were testing, or if it was just a normal variation within a population of various groupings, of various sample sizes. And there are many types of questions researchers could be testing. Like they could be testing a medicine. They could be testing, is the earth warming up? Does a public prefer a certain color for a new fashion line, whether we want to, get that color going or not? Is a new teaching method better than a traditional one? And different things that researchers could be testing. And it's a shame that often we find that they make this claim that it was so much better, and then we really find out later, well, really maybe not. It wasn't all that much better. But if they do their hypothesis testing correctly, then they should be able to be pretty sure. Now, there are some errors they can make in that decision-making process, and we'll talk about those. There's the traditional method, the p-value method, and the confidence interval method used to test hypotheses. In the traditional method, you have a statistical hypothesis, and that's a conjecture about the population parameter, often the mean, because that's something that it's easy to look at. And the conjecture may or may not be true, but they're stating a hypothesis. Now, the hypothesis, again, it could be true or it could be false. Now, this null hypothesis right here is something that you want to know the definition of, and it's symboled with H with a subscript of 0. It's a statistical hypothesis that says there's no difference or there's no change between two parameters. The alternative hypothesis will be symbolized by this H with a subscript 1, and that states that there is a difference between two parameters. And so we need to be able to state a null hypothesis and an alternative hypothesis. And I think on your test I have you state the two hypotheses, at least in one of the problems. You don't have to do any work. I just want you to state, the two different hypotheses. Now, here's just what I mean. You have a medical researcher interested in finding out whether a new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after a patient takes the medication? The researcher knows that the mean pulse rate for the population under the study is 82 beats per minute. So what are your two hypotheses? Well, the hypothesis, the null hypothesis right here, it says that the mean is 82 and that this is not going to cause a change. The alternative hypothesis, maybe I ought to make that a different color. I should have to start with. The alternative hypothesis here states that the mu is not equal to 82. It could be higher or it could be lower. Either one is a change. And so that's called a two-tailed test because a change can be on either side of the mean, either significantly higher or significantly lower than the mean. Now, in situation B, a chemist invents an additive to increase the life of an automobile battery. The mean lifetime of the automobile battery without the additive is 36 months. So, H sub 0, your null hypothesis, then, is that mu is equal to 36 months, or 36. The alternative hypothesis is that the average will be greater than 36 because what he wanted to increase the life of the automobile battery. So that's the difference they're looking for. Before, remember, it was just changing it. It could be lower or higher. And so this is called a right-tailed hypothesis test when you're looking for the increase. Okay? So this word increase here makes it a right-tailed test because to be successful, it's got to increase the battery life. Now, in the next situation, a contractor wishes to lower heating bills by using a special type of insulation in houses. If the average of the monthly heating bills is $78, her hypothesis about the heating costs with the use of insulation are the null hypothesis, which says that the average is $78 and that the insulation is not going to make a change. And the alternative hypothesis is that the heating bills will go down. They're going to lower the heating bills. So that means it's got to be less than 78. So the key word here, lower, means we want something lower than the mean or to the left side of the normal distribution. And so that's why it's a left-tailed hypothesis test. So you can have a two-tailed test, a one-tailed, and that can be either left or right, less than or greater than the mean. Now, when a researcher conducts a study, she's looking for evidence, or he is looking for evidence to support a claim. And the claim is usually the alternative hypothesis or the research hypothesis. But it could be, and sometimes it's encouraged, that researchers state their claim is the null hypothesis. And one reason for that is because then they don't show, supposedly that helps them remain more impartial. They don't predict a desired outcome and maybe unconsciously do something to make the outcome fit their hypothesis. And so if they state the null hypothesis, the idea is that sometimes their data will be more impartial. Statistical evidence can support the claim, and that's all it does. So if you support the null hypothesis that there was no change, then you're basically saying that whatever you're testing did not do any good. So if you, in that case, if your testing is a success, you'll reject your hypothesis because there was a significant change rather than no change, which you stated as the null hypothesis. So you have to, it takes a little thought to get some of this kind of straight. So you would want to reject the claim if the claim was the null hypothesis, again, in order to show that whatever you're testing made a significant difference. So you have to watch what you're doing in that, how you state your research hypothesis and whether or not your claim is rejected or supported. Now, after you state your hypothesis, you design your study, you figure out your correct statistical test, and there are many more than we'll go over in this course. There's a lot of statistical tests. You choose an appropriate level of significance. Now, this level of significance is going to be important. Whether you're 90% sure, 99% sure, that sort of thing, that your claim is supported or not supported. And you formulate a plan for conducting the study. The statistical test is going to use the data that you obtain from the sample that you test. You make a decision about whether the null hypothesis should be rejected or not, or supported. And the numerical test obtained from a statistical test will be your test value. In this hypothesis testing situation, there are 4 possible outcomes. And this, to me, is a confusing chart. But I think there's an example in the book that makes it maybe a little clearer. That one error, type 1 error, is when the null hypothesis is true, but you reject it. If the null hypothesis is true and you support it or do not reject it, right here, see this, here we show the null hypothesis is true and we do not reject it, then we've made well, I'm a little concerned. I see that my recording had stopped and I'm not sure where it stopped. So I'm going to go forward from here and hope I haven't skipped too much or lost too much. This is a picture that shows the errors that can happen in this hypothesis testing. And it's a little confusing, but there is something in the book that perhaps will help a little bit. If you reject, if the hypothesis is true, and if the null hypothesis is true and you reject it right here, then you've made a type 1 error, because you should have, if it's true, it should not reject it, you support it. So this, if the null hypothesis is true and you don't reject it, then you've made a good decision. Now suppose that the null hypothesis after we do our testing is false. Well, then if the null hypothesis is false and we reject it, well then that's a correct decision. But if the null hypothesis is false and we don't reject it, then we've made a type 2 error. Now that sounds all very confusing. What is type 1? What is type 2 error? And those definitions are in your book. A type 1 error occurs when we reject the null when you should have kept it. And a type 2 error occurs if you do not reject it when you should reject it when it's false. Now, there are some, there's something in the book that I think helps a little bit in maybe making this a little clearer. And in the book, it shows, for example, your null hypothesis, if you have a jury trial, okay, that your defendant is innocent. Okay. And your alternative hypothesis is that your defendant is not innocent, or that they're guilty. So in other words, that they're guilty. And when somebody's on trial, they're either convicted or they're acquitted. So let's go back here, and we're going to put that our null hypothesis was true, so that means that they're innocent here in this section. Okay. And if the null hypothesis is false, then they were guilty, because the null hypothesis was the defendant was innocent. Then we're going to go over here. If the null hypothesis is rejected, in other words, if the defendant was innocent and you convict him, the jury convicts him, they've made a mistake. They've made a mistake. If the defendant was innocent and he was acquitted, then they've made a good decision. So that's the idea of where we can come up with the idea of, I think that helps. It helps me to understand what do we mean by, instead of just saying null hypothesis and reject and keep. Think of it in terms of something you can see where the mistake was made. Okay, this person was innocent, but he was convicted. Well, that's a mistake. That's a type 1 error. If he was innocent and he was acquitted, well, the jury made the correct decision. On the other hand, this is not, why did I put false? What I want to put here is that in this case, he was guilty. Okay. So if the person was guilty and they convicted him, well, again, they made a correct decision. But if he was guilty and he was acquitted, and that happens as well, then the jury made a mistake. So you're the jury, you're the researcher. You make the decision when you analyze your data. And you might make a mistake. You might say, I think it made a significant difference when it really did not. Or you might say there was no change when there really was. And so those are the sort of things that you deal with when you are looking at your testing, your hypothesis testing, because you're the researcher, you've done an experiment, and now you're going to decide if it was what your data is telling you. So, when you're doing hypothesis testing, let's see, somehow I got that in all the wrong place, so, oh, I see. Let me go through and click on here what I've gone through already. And hopefully I didn't leave too much of this out. There's that slide I was looking for. Okay, we already went over that again. Now, the level of significance. The maximum probability of committing a type 1 error. This probability is simplified by A, or a Greek letter alpha, and we're just for type, it's A. If you're writing alpha in handwritten looks more like that. Okay? And then beta, handwritten, looks more like that. So, in case you need to know or see that written out. Alpha is the probability of committing a type 1 error, and beta is the probability of committing a type 2 error. Okay. Typical significance levels that we look at is are 0.1, 0.05, and 0.01. For example, 0.1, there's a 10% chance of rejecting a true null hypothesis. So if you've got 0.1, that means 90%, okay, or you've got a 90% chance of not rejecting a true null hypothesis. So those are the levels of significance that you're going to work with most often. 0.1, 0.05, and 0.01. Okay? And there's corresponding z-scores for those regions, for those tests. And you'll see those in your book for the most part. And it's different whether it's right-tailed or two-tailed. So, kind of look over in your book about those, and we'll work through a couple examples. The critical value separates the critical region from the non-critical region. So you've got your and we have some pictures. So you've got your bell curve. The critical value is going to be your z-score that you're going to use. The critical region or rejection region is one of the tails. Okay, and the non-critical region or non-rejection region is going to be the larger part that's under the middle a part of the bell. So these are going to be in the tails. Your rejection region, your critical region, or those are going to be at one tail or either one or both tails. Critical value here is going to be your z-score that corresponds with those level of significance, and the non-critical or rejection region is going to be in it's going to be more of the middle. So if I was going to draw a bell curve here, sort of in here, okay, and there's my mean right in the middle, and I have this right here, that's going to be your, let's see if I can do this. Okay, no, I don't like that. That's too. Let me just change the color of my pen and try it that way. Okay, there's your critical value right there. Okay, and so I'm going to highlight that in green. That's your critical value. The critical or the rejection region, I'm going to highlight in yellow, and that's going to be this down here. This would be a left tail test. And the non-critical or non-rejection region, okay, would be this whole part of the curve up here. The non-critical or non-rejection region. And this would be if this was a left-tailed test. If it was two tails, then obviously the critical regions would be on either end. So this one is a left-tailed test. And this is just an example that I've drawn, but hopefully it will help you a little bit to see about what I'm talking about when we say these things, and give you a little color coding on what we mean. Now here's finding the critical region for alpha 0.01 right-tailed test. That means there's 0.01 in the right tail, which means you've got 0.99 over here to the left. All of this is 0.99, and your critical region is what's just highlighted in yellow. So 0.99, the closest thing we can get, is right here in our, again, this is our Z table, and so we have 0.233. So our critical value then, so this Z-score here is our critical value. Let me find that. And this one's a right tail test rather than a left tail test, because we're looking for greater than the mean at this level for this critical level of significance. And again, alpha is the level of, that's your level of significance you're looking for. Now, find the critical value for alpha 0.01 left tail test. Well, because of the symmetrical nature of a bell curve, we know that this Z-score here is going to be the same as the one on the previous slide. And again, that is your critical value. That Z-score is your critical value, only this time it's a negative 2.33 for a left-tailed alpha of 0.01. Here we've got an alpha 0.01 two-tailed test. Well, If alpha is 0.01, it's still 0.01, but now it's divided into two tails, so each tail is 0.05. Okay, so that's going to be a different. We have to look, and we've still got the 99% between the curves here that we saw before. That hadn't changed. That's still 0.99. But now we've got two tails. So in each tail, instead of 0.01, since there's two, that's 0.005. So we go back to our Z table, and you find that our critical value is 2.58. So in this one, then, your critical value is your negative, it's plus or minus 2.58. That's a Z-score. Okay? So, once you find the critical value, depending on what level of significance is stated in the problem, you draw your figure, draw your bell curve, label it just like you've seen in these pictures, color in whether you're looking for your left tail, your right tail, or two tails. Again, remember, if the test is two-tailed, you have to divide by 2. That's important. You have to divide alpha by 2 to find the Z-score. And most of the Z-scores are going to be the same. You'll get used to using which ones go with what level of significance. Then you're going to find the critical values for a specific alpha. Again, that's your level of significance. Use the table. Find the Z value that corresponds to the area. For a right-tailed test, it's going to be 1 minus alpha. For a left-tailed test, it's going to be just the value. Because remember, on the Z table reads the area to the left of the Z-score. So, the bottom one you just need to find the area. The top one you need to subtract it from 1 because it's the larger percentage of it that's to the left of the Z-score. And for a two-tailed test, you're going to be sure to do the alpha over 2. Okay, we're looking at an example. Using table E, find the critical value for each situation and draw the appropriate figure showing the critical region. A left-tailed test with an alpha of 0.1. So when we look in table E, you find that the closest area to 0.1 is 1.003, and there's 0.9. That means there's 90% of the curve above it here, and this is our critical value right here, which is your Z-score. And there's 10% of the curve to the left. And you highlight, shade that in, and the Z value is 1.28 based on looking up on the Z table. Now on step B, you want a two-tailed test with an alpha of 0.02. Well, you divide that by 2, so you have 0.01 in each of the tails, 99% between them. And we've already looked up 0.01 before, but you find the areas closest to 0.01 and 0.99. And that comes out to be, you have two critical values on this one. There's a critical value here of negative 2.33. That's your critical value. And your critical value here is 2.33. Those are your Z-scores. And remember, 0 is always in the middle. Okay. And then we have example C, a right-tailed test with alpha 0.005. Well, that means we have 0.995 to the left of that value. You subtract 1 minus 0.005. So this is the value that you're going to look up in your Z-score, in your Z table. So the closest you can get, you have 0.9949 and 0.9951, which gives you z-values of 2.57 and 2.58, which is 2.575. So your critical value here is going to be z is 2.58. Okay. And that's a CV. It looks kind of... Okay. Now here's the steps for the procedure. State the hypothesis, state the claim, identify the claim, find the critical values from the appropriate table from the problem, compute the test value, make the decision to reject or not reject the null hypothesis, and then step 5 is going to be to summarize your results, which means you're going to say, you know, we rejected or we did not reject the hypothesis. And I believe, yes, that's it. So hopefully we'll get into an 8.2 working some actual problems and more than just kind of learning about some of the vocabulary. But this vocabulary are things you need to know, and get that straight in your mind, and try to have what type 1 error and type 2 error are. There's not going to be very many questions about that on this last test because it is kind of confusing. But you need to have an idea at least of why we're concerned about making an error in either direction.